We have discussed resistive method for deposition of thin film. The next method is sputter deposition. In the sputter deposition technique, the concept we are using is momentum transfer. A fast moving ion or atom is coming and hitting on the surface of the material or the target, which is to be ejected and deposited on the substrate. So we are imparting energy to the incident ion by applying electric field. So let us see the cases. First, let us see the incident ion, which is coming here with slightly less energy. It is coming and hitting on the surface. This is the surface of the target atom. On the surface itself, it is getting reflected because it is of less energy. When this ion is getting reflected, it can simply get reflected as the ion itself, or it will absorb one electron from this substance, target substance, and become neutralized. Again, it is only getting reflected back. Now you increase the energy of the incident ion slightly more. What happens is it will cause emission of secondary electrons. Secondary electrons will be knocked off from the target material. This is the target material. So because it has got slightly more energy, it will knock off secondary electrons. Next, if you increase the energy of the incident ion further, it can just penetrate the surface. When it is just penetrating, it has got sufficient energy to just penetrate the surface. It will cause structural changes in the material of this is the third case. So it will cause structural changes. These are the atoms of the target material. I have drawn them far apart, but these are very close to the surface. So this ion will interact with the atoms on the surface and cause structural changes to the target material. And the ion that has just entered the surface, it will get terminated or it will stop very close to the surface. This is very close to the surface. I have drawn it big. So this is getting implanted in the target material. Now if you slightly increase the energy of the incident ion further, it will have sufficient energy to eject atoms from the target materials. These are all activity taking place very close to the surface. It will knock off the atoms from the target material. So it will come out as the sputtered atom. So this sputtered atom, it is knocked off in all possible directions. So if you enclose this in a chamber, you are placing a chamber like this. So it can, and you are placing substrate somewhere over here. These atoms can go and get deposited on the substrate and thin film deposition is possible. If the energy of the incident ion is still further high, what happens is it will penetrate deep into the target material. So it won't be able to knock off atoms from the deep inside to outside to get it sputtered. So the amount of sputtering will decrease if you increase the energy of the incident ion further. It will go deep inside the target material and get implanted or embedded inside that target material. So if you look at the yield we are speaking in terms of average number of atoms ejected per incident ion. How many atoms are ejected depending upon the number of incident ions. You can see that when you increase the energy, this is increasing, and up to a certain energy, the number of atoms ejected increases. That is the region where you have this sputtered atom. Further you increase the energy, the ion is getting implanted or embedded inside the target material, and the sputtered atoms, the number will decrease, so the yield will decrease. So this is the sputtering yield versus ion energy graph. This is another graph showing the velocity of the sputtered atoms. This is the velocity of the ejected atoms. I don't say sputtered because we are comparing with the evaporated technique and sputtered technique. The velocity of the evaporated ejected atoms versus the number. So this is in the case of the evaporated case. In the sputtering phenomena, we have the velocity of the atoms greater. Once we have deposited films, we need to measure the thickness of the film. There are different methods of measurement of thickness. One is the electrical method and you have the optical method. These two methods are the commonly used techniques to determine the thickness of the film. First, let us look at the resistive measurement. You are measuring the resistance to determine the thickness. So this is using the 4-probe method. 4-probe method means you are placing the sample on a board like this. You have 4 connecting leads or 4 probes are there. These 2 are for current and these 2 are for measurement of voltage. The spacing between these 2 terminals is S. Current is coming, this is flowing out, 4 pin-like arrangement is there. Between these 2 contacts you measure the voltage. So you are placing the thin film here where the probes will get contact with that, and the resistance rho is given by the formula 2 pi s V by I, where S is the spacing between these 2 probes, V is the measured voltage, I is the current. If the thickness of our film is very much less than half the spacing, S is the spacing between these 2 probes. If the film thickness is much less than S by 2, we can use the formula rho equal to 4.53 Vt by I. So rearranging this, you can determine what is the thickness of the film. And the quantity rho is the resistivity. Rho by T is also called the sheet resistivity of the film. Another method using the electrical technique is the Wheatstone bridge arrangement. Wheatstone bridge arrangement, you know, we have 4 resistances P, Q, R, S, and you can balance the Wheatstone bridge and determine the resistance in each arm. Here we are placing in one of the arms the film whose resistance we are measuring by this arrangement. We are enclosing this entire thing inside our vacuum chamber. You have a source. This is a shutter. Initially you keep the shutter closed, and when you start the experiment you can open the shutter from outside. This is the substrate over which from the source the material gets evaporated and the film is deposited. So as the film is being deposited on this, the resistance of this arm S will change. So this change in resistance can be measured, and from that resistance proportional to thickness, you can calibrate it and determine the thickness. So this is an indirect method of determination of thickness. Coming to the optical methods, one is the quartz crystal monitor method, which is the most commonly used method. So I have just drawn only a schematic diagram. A whole setup is enclosed in the vacuum chamber where you have the thin film deposition. Here I have placed the resistive coil. This is the sample. You apply electrical potential, sufficient heat is generated, and this material get evaporated. A shutter is placed over here. This is the substrate over which you deposit the film. I am placing 2 quartz crystals. One is in this place just above the shutter. When you are opening the shutter, only the substrate region is opened. This quartz crystal region, the shutter is not opened. Another quartz crystal is here which is directly exposed to the evaporants. So it will receive the same amount of material to be deposited as that of the substrate. So the thickness of the film that is deposited on the substrate and the quartz crystal will be, we are assuming it to be the same. And this will have the initial thickness itself. The mass is density into volume. So mass of the film can be expressed as density into area into thickness, because T is what we require to find out. Now, the quartz crystal which is placed over here, it has got a resonant frequency. Its frequency is velocity by lambda. If you look at the quartz crystal like this is the thickness of the quartz crystal, and these 2 sides are fixed. So it will have nodes at these 2 fixed ends. So the first mode will have the thickness will correspond to lambda by 2. So T I can write, lambda I can write in terms of 2T, because I have to express the equation for frequency. Instead of lambda I can write 2T. So 1 by 2T into root of velocity in terms of shear modulus. So this is root of C by the rho Q is the density of the quartz crystal. So this is the resonant frequency initially of the quartz crystal, which is placed in both these cases just before the start of the deposition. Once the deposition is completed, the frequency of this crystal will change, whereas this will remain the same. The shift in frequency of the quartz crystal which is exposed to the film deposition is expressed by this formula. This quantity 2f naught square by root of C rho Q. This is a constant that is equal to Cf, which is a constant for that particular crystal. So m mass by area in terms of density and thickness we have expressed. So rearranging this, you can find out the thickness of the film. This is the quartz crystal method, which is the most common used technique.